Hello, I'm Dr. Jim Woodburn, Chief Orbital Scientist at Analytical Graphics, and today I'm going to be talking to you about preparing your flight dynamics team to fly your satellite mission. Okay, so there's been a lot of different trends that we've seen recently with respect to flight dynamics teams, and the operation of spacecraft in general is very, very different than when I started quite a number of years ago, where we had a small number of spacecraft that we were flying, and we had a very large orbit analyst shop, and people thought that what we did was magic, and we perpetuated that philosophy by wearing wizard hats while we did important activities. But nowadays, flight dynamics is seen as much more of a commodity. We're seeing much smaller teams being involved in operating spacecraft. And we're also seeing a lot of new players in the space field, where previously it took huge programs to launch any type of satellite almost. Nowadays, we're seeing things like the Koreans and the Israelis putting together missions to the moon. So that type of robust and very exciting mission is becoming more commonplace. We're also seeing commercial space just exploding. Huge constellations being proposed. OneWeb will be launching soon. SpaceX is proposing an even larger constellation of satellites. So we're talking about, 2 constellations that will involve thousands of satellites, when added together. So lots of things are changing. The flight dynamics, a lot of the times nowadays, is done by a very small team of people. Sometimes not even in the same location, right? You can be distributed, you can be running your flight dynamics operations over the web. So it's very different than it was, say, 20 to 30 years ago. One thing is still the case, though, is that we want to be prepared, right? These missions are special. They have unique characteristics typically. They have sometimes very long lead times to flight, things like the James Webb Space Telescope, for example. So we still need to get everything right once we launch the mission. And to do that, what we want to do, of course, is to be prepared for the types of things that may happen. And that preparation comes both in terms of our specialized teams involved in operating the satellites and our integrated team. So of course our flight dynamics team needs to be prepared for the types of challenges that they may face, but also this whole spacecraft operations team together has to be prepared to address challenges as well. So for example, my flight dynamics team may be well prepared and know their procedures in order to address a specific anomaly. However, addressing that anomaly may require a certain decision to be made, and if we don't know who has authority to make that decision, right, we get stuck. So we have both a need for our specialized folks to know their jobs well, and a need for the entire team to be able to work together properly. So typically when we prepare for a mission, we spend the vast majority of our time preparing for the special activities of the mission, right? So we have a launch, we have maneuvers, we have all kinds of other, very specific activities that go on, and we spend most of our time working on preparing for those type of activities as opposed to nominal operations. And that's justified because special activities are really when our spacecraft is at the most risk. And I've put up numbers saying that 5% of the mission timeline requires 95% of the prep. I made that up, of course. And the point is simply to say the vast majority of your prep goes towards a very small percentage of the time. But that very small percentage of the time is really critical events. And so, of course, the thing we want to do again is do everything we possibly can before launch to make sure that things go smoothly after launch. right? We can practice things 100 times before launch, but once launch happens, we only have one chance to get it right. So an activity that I've been involved with a few times on different missions, known as operational readiness tests, have really proven to be very, very effective in terms of preparing the operations teams for the launch of the spacecraft and for allowing the development of operational procedures, exercising the command chain, making sure all the data flows work properly, and really giving the operators a sense of readiness, right? Because not only do we prepare the operators for what they're about to experience with the launch of the mission, right, which is good from a technical sense of, okay, they know what to do, but they also feel like they know what to do, which is sometimes equally important. Oh, and yeah, an added bonus of this particular technique is that when we prepare our operators in this way, it also establishes a methodology that we can use later on if the mission changes. So we're going through a whole bunch of different events. We're teaching our operators how to deal with anomalies, and that also prepares them for mission changes, which happen sometimes by necessity because of failures on the spacecraft, sometimes because our spacecraft has performed so well we want to go and do an extended mission, which requires the spacecraft to operate in a new way. Okay, so what types of events do we need to prepare for? Does anybody in the audience recognize this particular event? This is from the Star Trek series and is, of course, the infamous Kobayashi-Maru scenario. So in the Kobayashi-Maru scenario, we're aboard the Kobayashi-Maru, which is a spaceship, and we're aboard a Federation ship. We've received a distress signal from the Kobayashi-Maru, which is in the Klingon neutral zone. The goal is to get to the Klingon neutral zone and rescue the crew of the Kobayashi-Maru before the Klingons show up and bad things happen. Of course, by the time we get there, the Klingons are already there, and we're presented with a no-win scenario and everybody dies. This is not a particularly good type of scenario to train the operators on, right? No-win scenarios, nobody learns anything. We don't want to demotivate people, we want to motivate people. So what do we want to do in reality, right? Well, what we want to do is we want to produce realistic simulations, simulations of realistic events that can happen, things that we've seen before, and we want to make sure that what we're doing is actually preparing the operators for what they're about to see and experience. An additional pitfall that we can fall into, though, that we have to be careful about is the potential for generating unrealistic simulations. And unrealistic in this sense doesn't mean something that can never ever happen. It means that I'm presenting the operators with data indicating an anomaly, but the data is not consistent with my operational models. So what can happen in that type of a situation is I can spend a lot of time, waste a lot of time, really in a time-critical period of mission prep, trying to chase down problems which are being caused by the fact that the data I'm pushing into my operational system is not realistic, and it causes the operational system to choke, and that's what I'm looking at. I'm not chasing down the actual anomaly I'm trying to simulate. And we see this sometimes when, let's say, Fred's engineering tool is used to generate data for a specific type of mission event. But it has perhaps a bunch of approximations in it, which makes the model not very realistic. And of course, our operational system is meant to deal with real data, so we need to push realistic data through it. So this is definitely a risk that we don't want to take. We don't want to spend our time chasing down red herrings. We want to spend our time training the operators for realistic types of contingencies. So the types of flight dynamic systems that I've worked with during operational readiness tests have been based on STK and ODTK. And these types of systems are really nice in that for the operation side of things, you're typically dealing with the engine version of the products, right, where the product's capabilities are hidden behind an customized operational workflow that the operators use to be able to do just what they need to do every day. But in the case of things going bump in the night, right, something went wrong, we have the ability to pull the scenarios, the STK scenarios and ODTK scenarios out of the operational system, bring them up in the desktop products, and be able to do a much more detailed analysis in the desktop products because of the level of flexibility that the desktop products bring us. Well, this level of flexibility is also key in enabling us to design simulations, right? So we can take all of the capabilities of STK and ODTK and apply them to generating realistic anomaly conditions that we can then push back through the operational system. Because we're using the same tools that the operational system is built on, we don't have this issue of potentially having model mismatches, right? We're not going to end up chasing model inconsistencies instead of trying to diagnose the anomaly that we're trying to simulate. So in specific, with STK, typically what I'll use that for is to generate maneuver errors where I want to simulate a specific effect. And what I mean by that is perhaps I want to simulate, perhaps I have a large mission maneuver coming up and I want to simulate a case where the maneuver gives me a semi-major axis length at the end of the maneuver that's 2 kilometers low of where I want it to be. Right? That's very easy to do in STK. Using astrogator, I can just target a semi-major axis length that's 2 kilometers smaller than the nominal. On the other hand, if I don't really care what type of maneuver error I'm generating, and I just want to generate random maneuver errors, I can do that directly in ODTK. In addition to generating maneuver errors in ODTK, I can also add tracking data anomalies on top of things. So I can vary range biases or add, jumps in the transponder delay. Make the measurement noise much larger than what it's expected to be. And in either case, whether I'm using STK, ODTK, both, whatever, I also have the ability to either generate a continuous mission timeline, say with a specific anomaly associated with each event in my mission timeline, or perhaps some events don't have anomalies. And I can have my operators run through the entire mission, or I can take one specific event in the mission and cycle it many times. So, for example, if I am going to the moon, the biggest, most critical event typically on a lunar mission is the lunar orbit insertion maneuver. This is where everybody gets really nervous, right? We're going to fire the engines, and then a lot of times we're going to go behind the moon, and we're not really going to know what's happened for a while. So in that type of situation, I might want to drill that particular event many times with many different types of contingencies involved. Speaking of lunar missions, the example I'm going to show to demonstrate this process is LADEE. LADEE was a lunar orbiter. I supported the operational readiness testing for this mission, one of the big benefits was that we got to write a technical paper and go to a conference. Well, of course, in addition to preparing the flight dynamics team. But one lesson I learned is if you do write a technical paper based on your experiences and go to a conference, be selective where you submit your paper, because we submitted ours to the Spaceflight Mechanics meeting in Williamsburg, Virginia in January. Williamsburg, Virginia is not where you want to be in January, right? You want to go to Maui in January. Williamsburg, Virginia in the summer might be okay, but just a little word to the wise. Select your conferences, with some forethought. Okay, so this is a depiction of the data flow throughout the LADEE operational readiness tests. And if we look down here in this corner, in this blue ellipse, This is the area where we generated our simulated information to drive the test. So we generated simulated trajectories, simulated tracking data based on those trajectories, and then that information was pushed into the rest of the test, both pushed into the flight dynamics team and pushed over here to the spacecraft simulator. So the important point there was that we were using the same truth trajectory for that we generated for the simulation to drive both the creation of observational data and to go through the spacecraft simulator, so that when simulated telemetry was produced, the simulated telemetry agreed with what we produced in the tracking data. Right? So once again, we're not trying to trick operators by doing something that's impossible. We want to keep things consistent and allow them to attack the anomalies that we want them to see. So then here in the purple area, this is the scope of the flight dynamics team. And so they would receive the simulated tracking data, and then they would have to deal with it. And the important point here is this developed basically two different realities, right? We had our truth reality, whatever we're generating down here in the blue, and to drive the system in terms of trajectories and tracking data. And then here in the purple, the flight dynamics team is producing an alternate reality, right? It's the reality as perceived by the spacecraft operations team. So they are generating estimated trajectories, and those estimated trajectories are what's going off and being used to plan the rest of the mission and so forth. So just like in a real mission, right, we never know what truth is. The flight dynamics team never knew what truth was. We never told them. But they only knew what their perception was. And so this is a different way of depicting that. Up on the top, we have where we're generating our simulated truth, right? So that's our one reality up on top. And then our other reality, which is the perceived reality by the operations team, is on the bottom. So on the top, we're entering maneuver errors and all into our trajectory. We're generating tracking data and so forth. And that information, the tracking data information, is going off to the operations team. The truth trajectory is going over to the spacecraft simulator to be used in generating simulated telemetry. Then down here in this box, what we're seeing is the spacecraft operations team now processing that tracking data, creating their perception of what the truth is. They, of course, are assuming maneuvers are going as planned until the tracking data tells them otherwise. They're creating an estimated orbit, and that estimated orbit is going out to the rest of the spacecraft operations team for all the subsequent activities. And this is a little bit more detail in terms of the tracking data generation itself. What we can see is that we have our simulated orbit trajectory, and then during the ORT period, we're adding things like jumps in observation biases. We may change the transponder delay, environmental mismodeling, increased noise on the measurements, and so forth. So this added additional challenges to the spacecraft operations team for when they process the data. So here are some of the trajectory challenges that we presented to the LADEE team. Things like a unexpected and errant reaction control thruster firing, unexpected variations in the solar pressure effects on the satellite, and so forth. Kind of a not unexpected, but just a particular perturbation in one of the primary maneuvers. And then on the tracking data side, we did things like changing the transponder delay, actually giving them a very large transponder delay that they weren't expecting at all, a random change in a range bias, degraded tracking, and a whole variety of things. So here's a few examples that came out of the ORT when the operations team processed the data. What we see here is we see an increase in the random variation of a range bias during a tracking pass. So once again, this is a residual ratio plot up here, and what we see is the range bias pushing the observations out of the acceptable range here for a while. Over on this side, what we're seeing is a random variation in the range bias itself. So a large constant was added into the range bias, which caused the rejection of all ranging measurements across a particular pass, followed directly by a large increase in the measurement noise on the Doppler measurements. And down on the bottom, we see a particular example where we did a 7% hot burn, and we see the ability of the operations team here to recover that. Okay, so we presented them with a whole variety of different challenges during the ORTs, and they really did a great job in recovering from all the different things that we presented to them. And kind of as an outcome of all this, right, or I shouldn't say an outcome, but related to all this, when they actually did fly the mission, they actually did detect a significant transponder delay that they didn't know about, and they also had a case where one of the ground stations was misconfigured on an early pass of the satellite and had a very large and unexpected range bias. So both things that were covered during the ORTs, so they were familiar with the signatures of those types of contingencies, and were able to, work through them during real operations. And that's all I have for you today. I hope you enjoyed this presentation. Once again, I'm Jim Woodburn, Chief Orbital Scientist at Analytical Graphics.